Yes, sir. Yes, sir. Yes, sir.
Okay, okay, okay. So that is the main. So now that is the main problem of the earlier method. So it cannot handle multiple words with multiple meanings. It cannot handle, and that is why we have to consider the concept of the self attention, and that is used in the transformer. So you can see here, I am giving one example. Consider two sentences: river bank and a money bank. In river bank, the word bank refers to the side of the river. In money bank, bank is nothing but the financial institution. So, but in traditional word embedding, it's the same meaning, same representation. So that is why we have to consider the contextual embedding. So one is the river bank. So bank means the side of the river, and money bank means the bank is nothing but the financial institution. So that is why we have to see the contextual embedding. Static embedding is converted into contextual embedding by considering the self-attention. So static embedding can be converted into contextual embedding. So for this, actually, already I discussed, we have to find a similarity between two vectors. So here again, we are considering the dot product. So we are considering these two examples: money bank grows and river bank flows. So corresponding to this, we are doing the embedding for the money. So E new, embedding for the bank, that is a new embedding. E new grow, that is the embedding for the word grow. And similarly for the river bank flows, so embedding for the river, the new embedding for the river, new embedding for the bank, and new embedding for the word flow we are determining. And that is actually the dot product we are considering. So dot product is nothing but the similarity score we can determine, that already I have explained, because we have to consider the two vectors. So you can see point 0.8, point 0.3, point 0.2, these are the similarity scores we are considering. And we are considering the new embedding. So embedding for the money, embedding for the bank, embedding for the word grow, embedding for the river, embedding for the bank, embedding for the flows we are determining. This is based on the dot product. So you can see, so we are considering this money bank grows. So what we are considering, we are finding the dot product between e bank and the money. So this dot product multiplied with e money. And similarly, eBank transpose, that is the dot product between the embedding vector bank and the embedding vector bank we are finding. And after this dot product we are determining and multiplied with eBank. So in this representation, if you see, one is actually, I can say query, another one is I can say key, and one value I can consider is a value we can consider. So in this representation, the dot product between the query and the key we are considering, and it is multiplied with the value. So we are doing this one. So this is the representation of the self-attention. So we are finding the dot product between the query and the key, and it is multiplied with the value, and that is the representation in the self-attention. So you can see corresponding to static embedding. So we have the static embedding e-bank, and we have some learnable metrics. WQ is a matrix, learnable matrix, that is with the help of the back propagation training. WK is a matrix and WV is a matrix. So from the static embedding, we can get the embedding, the contextual embedding. So we are getting Q bank, K bank, and V bank. That means the query, key, and the value we can determine. So Q bank we can determine the query corresponding to the word bank. K is the key corresponding to the word bank, and V is the value corresponding to the word bank. So we are determining these embeddings. So that is actually the self-attention based on the matrix, the WQ, WK, and WV we are considering. So attention score we can determine by using this formula. So what you can do, you can see first we are doing the dot product between Q and K. So if you see the previous expression, I have shown this expression. So you can see we are finding the dot product between the and the key. And after this, we are multiplying with the value vector. So if you see representation, query and the key, that is actually dot product of this query and the key. And after this, it is multiplied with the value. So here you can see in this expression, we are considering the dot product between Q and K. And after this, it is multiplied with the V. And we are considering softmax, we are considering. And this dot product is divided by root over dk. So dk is the dimension of the key vector, because we have to normalize this one. Otherwise, if I consider dimension is changing, suppose dimension is growing, so this value will be going high and high. So that is why we have to do the normalization of this. So to normalize the output of the dot product, we are dividing this dot product by root over dk. So dk is the dimension of the key vector, and after this we are applying the softmax, and after this you can see I am getting the attention. So attention is qkv we are getting. Okay, so that means for the word for the sentence money bank grows, we are determining q, k and the v, and after determining q, k and the v, we are determining the attention by formula. So attention qkv we can determine by using this formula. So first we have to take the dot product, and after this, to normalize the dot product, we are dividing by root over dk multiplied by v, and after this we are determining the softmax. Softmax we are applying. So if I apply the softmax, actually it is the probability value. So probability value lies between 0 and 1. So 0.9, 0.8, 0.7, these type of values we are getting. And these are actually the attention score. So 0.9, 0.9 means more attention. 0.1, so less attention. So that means we can find the contextual importance based on the attention score. So if the suppose 0.9 is the attention value, so that means what we can say, the attention is more, and we can see the relationship between two words in a particular sentence based on the attention score. So like this, you can see this figure. Again, you can see X is the input, and W is the WQ, that is the matrix, KQ and the V, WK, WV. So this is the matrix, and it is multiplied, and I'm getting QKV, I'm getting. So already I have mentioned. So multiplied means I'm doing the multiplications. And after this, you can see I am considering this, the dot product between Q and the K, and it is divided by dk, root over dk, and it is multiplied by V, the value. And after this, we are taking the softmax, and I'm getting the Z value I'm getting. So this process again I am considering how to determine the embedding. So that is actually that is the self attention. So you can see the money bank grows. So WQ, WK, and WV, these are the metrics, learnable metrics, and that is obtained with the help of the backpropagation training. And we are determining Q money, K money, and the V money. That is for the money. And similarly for the word bank, we can determine Q bank, K bank, and V bank. We can determine. And similarly for the word, similarly for the word grows, we can determine Q grows, K grows, and V grows. We can determine. And after this, after determining this, you can value S11, we are getting S12, you are getting S13, you are getting. And after this, we are doing the scaling. Scaling means root over dk. So that value is divided by root over dk. And after this, it is we are taking the softmax of this, and we are getting the value. V money we are getting, V bank we are getting, V grow we are getting. So this Y money we are getting W11 into V money, W12 into V bank, W13 into V grow. So what is actually W11? W1 is nothing but the dot product between Q and K divided by dk, root over dk, and we are taking the softmax. After this, we are multiplying with the value V money, V bank, and the V grow. So Y money is the new that is weighted sum of money, bank, and the grow. So W11 into V money plus W12 into V bank plus W13 into V grow. We are having this one. So I am repeating this. For these sentences, money, bank, grows, we are determining Y money, Y bank, and Y grow. We are determining. So first, what we are product between E, and I'm getting the value S11. S11 I'm getting, and after this we are, and also after this we are doing the softmax. That is the W11 I'm getting, and it is multiplied with the value and I'm getting this combination. So Y money is nothing but W11 into V money plus W12 into V bank plus W13 into V grow. I'm getting, and similarly Y bank also I'm getting W11 into V money, W12 into V bank, W13 into V grow. Like this, we are getting this embeddings. That is actually the final contextual embedding I'm getting. So like this, you can see in this example also I have shown. So first, we are determining key, query, and the value. So WK, WQ, and WP, these are the metrics. And input is how are you doing? And first we are doing the token embedding. So token embedding we have done. So these figures are taken from my book. Actually, these are some figures I have taken from my book. And after this, this WK, WQ, and the WP, these are the metrics. So we are multiplying these token embedding vectors with the metrics. And after this, we are getting the key, query, and the values I am getting. So corresponding to the input is the how are you doing. So first we are doing the token embedding, and after this, with the help of this principle, we are determining the alignment score. So alignment score is the EIJ is the alignment score we are having. So we are dividing by root over D model. So that is actually we are doing the normalization, because during the dot product the magnitude will be growing if the dimension is growing, if the dimension is more. So if the dimension is growing, then what will happen? This dot product magnitude will be also growing. So that is why for normalization we are considering divided by root over D model. That is the normalization we are doing. And we are finding the alignment score. Alignment score is the EIJ is the alignment score between ith word and the jth word. So that means I am finding the relationship between ith word and the jth word, whether they are related or not. If the probability value is very high, suppose 0.9, I can say there is a relationship between ith word and the jth word of the input sequence. If the probability value is less, very less, 0.1, suppose, I can say there is a very less relationship between the ith word and the jth word in the sequence. So that is the meaning of the alignment score. And if you see, this can be written in the matrix form. So you can see here. So one is the K, another one is the Q, and we are finding the E. E is nothing but it is Q and K is the dot product, and after this it is normalized, and E is the alignment score. So alignment score, it is written like this. And if you see the in the figure, we are having the alignment score like this, and in the diagonal lines you can see the alignment score is more. In the diagonal lines, the alignment score is more. And if you see other elements based on the intensity, you can see how are you doing. So alignment score, it depends on the position of the word or the contextual meaning of the word. Dr. Nayak, am I audible and slides are visible?
Yes, sir. Yes, sir. Visible, sir.
So after this, we have to apply the softmax we are applying. So softmax is applied after this, because already I mentioned that, because we have to consider the probability value. And if you see the expression j is equal to 1 to n, aij is equal to 1. So that means the probability, all the probabilities will be 1. So if you see this row wise, the probability will be 1. So these probabilities we are considering as 1. So in diagonal, you can see the high probability we are having. So how is related to how, R is related to R, U is related to U. Like this, the probability will be very high, that case. So in the figure, you can see we are having this, the input tokenization. First, we have to doing the, we are doing the token embedding. And after this, we are doing the multiplication with the WK, WQ, WV. And after this, we are considering the values, keys, queries, and the values. And we are determining the alignment score. And that's alignment score is nothing but the softmax we are considering. That is the probabilities we are considering. And we are finding the alignment score. So you can see, we are doing this one first, the token embedding we have done. And after this, we are determining the key, query, and the value. And after applying the softmax, we are getting the self-attention weight we are getting. So these are the probability values lying between 0 and 1. And you can see here, so first we are determining the self-attentions. And if you see the row wise, it is sum is equal to 1. Because already I mentioned the probability lies between 0 and 1. So corresponding to the input sequence, how are you doing? So we are considering key, query, this we are considering. And after this, we are determining the self-attention we are determining. And these are the probability values. And also we are determining the values. So these also we have determined. And after this, this is multiplied. You can see the self-attention score is multiplied with the value vector. And after this, we are having the context vector I am getting. So Ci is the context vector. So you can see how to get the context vector. This self attention is multiplied with the value. Aij is multiplied with Vj, and we have this context vector corresponding to the word u. So similarly, for other words also, we can determine the context vector we can determine by using this principle. So again, I am showing the same principle. So input is the how are you doing. Token embedding we have done. And after this, we have determined the queue, that key and the query we have determined also, and we have determined the value. And after softmax, I am getting the self-attention score I am determining. It is multiplied with the value, and I am getting the context vector I am getting. So this is the principle of the self-attention. So attention we can determine like this. So that means I am getting the context vector I am getting after these operations. I am getting the context vectors. So for this example, the bank is steep, so it is dangerous to stand near it. So query is it. So what is the meaning of query? Query is it. And key is the bank, steep, and the dangerous. So value means encode the meaning of the candidates, each of the candidates. The model, this model computes high attention weight between the query it and the bank and the steep, because it means the river. So you can see, so it is related to bank and it is also related to steep, and then aggregates their value to infer it refers to the river bank. So like this, it means actually the river bank. So that is why based on this score, that is the attention score, we can say, so it is related to river bank. So this is one example. After this next concept, already I mentioned, next one is the multi-head attention. So instead of considering only one attention, we can consider multiple attention, because we can see the part of the sentence or maybe the relationship between other words. So one attention may not be sufficient, but if I consider the other parts of the sentence or maybe the other words of the sentence, then instead of considering only one attention, we can consider multiple attention. So in the original paper, we have 8 attention blocks, Z0 to Z7. So that is actually attention blocks we have. So that means we have to consider okay. So you can see why actually we consider the multiple attention. So suppose if I consider one sentence, I can give one sentence. Maybe the sentence may be something like the cat sat on the mat. So if I consider only one attention, so one attention consider set on that, it may consider like this, but it may not consider set on the mat. So that is why we have to consider all the aspects, all the contextual meaning of the sentence and the word. So that is why we have to consider multi-head attention. So instead of considering only single attention, we are multiple attentions. So like this, here you can see why the single attention mechanism may not be sufficient in many cases. So head number 1, if I consider this sentence, the cat sat on the mat. So head number 1 focuses on cat sat. That is actually the subject verb relationship. Second head is cat on, sat on. That is actually the preposition handling. And head number 3 focuses on mat. That is the final location. So you can see how we can consider head number 1, head number 2, and head number 3 corresponding to this input sentence, and why actually we need multiple attentions. And that from this example you can understand why actually we need multiple attentions. So in the original paper, they considered 8 attention heads in the paper, the transformer paper. So here you can see we are considering this one. So first we have the hidden state. And this number of heads, actually, the dimension of the head, we can determine like this. The dimension of the head, D head is equal to D model, dimension of the model. divided by number of heads. So how many heads we can consider? So this should be divisible because we have to get the integer value. So D model divided by number of heads. So in the first figure, you can see we are considering 2 heads. And if you see the dimension of the model, D model, what is the dimension? 1, 2, 3, 4, 5, 6. So 6 divided by 2. So what will be the dimension of the head? So dimension of the head will be 3, 1, 2, 3. In the first figure, you can see we are considering 2 attention heads. So attention head 1 and attention head 2. And what is the dimension of the model? Dimension of the model in this example is 6, 1, 2, 3, 4, 5, 6. If you see the green circle, so how many green circles? 6, 1, 2, 3, 4, 5, 6. And what is the n head? The number of heads is equal to 2. So D model divided by D head. So n head, so it is 3. So it is 6 divided by 2 is equal to 3. So that is why the dimension of the head will be 3. In the second figure, you can see we are considering the dimension of the model is 6. You can see 6 green colored circles. And we are considering 3 attention heads. So D model divided by 3. So what will be the dimension of the hidden state? Dimension of the hidden state will be 6 divided by 3. So it will be 2. So like this, we can consider multiple heads. And after this, after getting this hidden state, we can do concatenation. So you can see h dash is equal to concatenation of this, all the heads. And it is multiplied with the one linear layer. W naught is the one linear operation we are doing. So one linear operation we are doing. And you can see the concept of the multiple heads. So here you can see D model we are considering, attention head we are considering. After this, we are doing the concatenation. And after this, we are considering one linear layer. So you can see the linear layer, it is considered W naught is a linear layer. And after this, we are considering the combined hidden states we are determining. So combined hidden state we can determine like this. So you can see here again I am showing where. So hidden states are available. After this, we are considering this D model, the dimension we are considering and number of heads we are considering. Okay, so now so again we have the states, and we have this the matrix WK, WQ, and WV, and we are determining the key, query, and the values we are determining. And after this, we are taking the dot product between the key and the query. And after applying the softmax activation function, we are having the self attention, and it is multiplied with the values, and we are getting the hidden states. That is actually the contextual vector we are getting. So to generate the smaller context vector, this projection matrix WK, WQ, and the WV, maybe we can consider of the size D into D head. So size of the projection matrix, maybe we can consider D model into D head. That size we can consider because what actually we consider smaller context vectors. If I want to generate the smaller context vectors, so what we can consider? We can consider the matrix WK, WQ, and the WV. The size will be D model into D head. So if you see WK is the D model into D head we are having, and I am getting the smaller context vectors. So smaller context vector we can determine like this. And in this figure, you can see I am considering the head, 3 heads we are considering, multiple heads, head number 1, head number 2, and head number 3. So actually we are not considering three different matrix. We are not considering. So if you see the portion of the matrix, here I have to take the pen. I will take the pen. Let me see this. So if you see here in the figure, so in the top portion of the matrix, this portion of the matrix, we are considering to compute the head number 1. And after this, if you see the second portion of the matrix, this is considered for determining the head number 2. And if you see the third portion of the matrix, that we are determining for head number 3. So instead of considering three different matrix, we are considering only one matrix. But the portion of the matrix it is considered. So you can see the first portion, that is considered for determining the head number 1. Second portion of the matrix we are considering for determining the head number 2. Third portion we are considering to determine the head number 3. Like this we are considering. So instead of considering many matrix, only one matrix it is considered. But the first portion of the matrix is responsible for the head number 1. Second portion of the matrix is responsible for the head number 2. And like this we are considering this one. So like this you can see we are determining K, Q and V value. We are determining after the shaping of this. And finally we are considering the attention value E dash we are determining. And after this, we are having the softmax activation function we are considering, and that is nothing but the attention score we are determining. And for all the heads, we are determining this because Aij, that is the attention score, is multiplied with the value vector. So what is C dash IJL? That is the attention score we are determining. That is mainly the multiplication of A IJK into V ILK. That is the multiplied. The value is multiplied with the attention probabilities. And after this, we are reshaping this. That is the concatenation we have done. And in the final, we are multiplying C with the W naught. W naught is the linear layer we are considering. So the W naught is the linear layer we are considering. So like this, you can see if I consider this in the tensor representation. So in the tensor representation, we can show multiple directions we can show. So hidden states we are determining. We have this hidden state. And after this, we are considering WK matrix, WQ matrix, and WV matrix. We are considering, and one of the portion of the matrix is considered for the one head. Second portion of the matrix it is considered for another head. Like this, we have to consider, and we are determining the key, query, and the values we have determined for the head number 1, for head number 2, and for the head number 3. And after this, you can get the output, and you can see in the tensor representations. You can see in one direction we are considering the number of heads, and D head is the dimension of the head we are considering. So like this we are getting the embedded, that output we are getting. So this is important for GPU implementation actually. For the GPU implementation we can consider the tensor representation of this. So in the TensorFlow also this concept is available. So this is the meaning of this. So finally we have to consider this. So hidden states are available. This matrix WK, WQ, WP is available, and we have to determine key, query, and the value we have to determine. And after this, we have to determine the alignment score for each of the heads we have to determine. So we are considering multiple heads, and we are determining the alignment score. Dr. Nayak, am I audible and slides are visible?
Yes, sir. Yes, sir.
So problem is actually I don't know whether network is connected or not. So that is why sometimes I ask.
No problem, sir. It's visible.
So this we are considering the alignment score, and after this, for all the heads, head number 1, head number 2, and head number 3, all the heads we are considering. After this, we are applying the softmax activation function, and we are finding the self attention score we are determining. And you can see the value also we have determined with the help of WV, that is the matrix WV is considered, and this value is multiplied attention. And after this, we are doing the concatenation, and W naught is the linear layer we are considering, and we are having the combined hidden state I am getting. So that is the combined hidden state I am getting. So this is the concept of the attention. So like this we can determine the attention, and these vectors we can determine. Next one is the position encoding is another important concept in number 6. So you can see these two sentences. One is the Omid kill lion and lion kill Omid. So if I consider only the self attention, then what will happen? There is no positional concept. If I consider self attention only, they will have the same meaning. But if I consider the positional encoding, actually these two sentences are different. So Omid kill lion and lion kill Omid. So the meaning is completely different. So that is why the position of Omid, the position of the lion in the sentence, that also we have to define. And that is done by considering the positional encoding. So without the positional encoding, if I use only the self attention, then these two cases cannot be distinguished. So it has the same meaning. Omid kill lion will have the same meaning as that of the lion kill the Omid, if I only consider only the self attention. So that is why the importance of the positional encoding. So the position of the Omid, the position of the lion, position of the kill, that word, That meaning we have to see in the case of the positional encoding. So that is the concept of the positional encoding. So for positional encoding, we are considering this. POS means the position, a particular position of the word in a sentence. So we are considering a sentence, and we are considering the position of the word in a particular sentence, and we are considering sine and cosine functions, and with variable frequency. The frequency is not same, so we can consider different frequencies. We can consider, and we can determine the position encoding vector. We can determine. So by using this equation PE pos 2I, so one is for the even, another one is for the odd. So 2I is the even and 2I plus 1 is the odd. So we are considering the sine function and the cos function. POS is the position of the word in a particular sentence. So that position also we are considering. And also we can change the frequency of the sine wave and the cosine wave also. We can change the position of this sinusoidal functions. The sine function and the cosine function we can change. So corresponding to these equations, PE pos 2I, that is the sine function we are considering, and PE pos 2I plus 1. So that means the second position. That second 2I plus 1 means the second position of the vector. 2I plus 1 is the second position of the vector. POS means the position of the word in a particular sentence. And we can determine this vector. The vector is the PK is the position vector we can determine. And if I consider the dimension of the model is 256, we can consider this vector PK vector we can determine. So you can see the dimension is plotted along the y-axis and positions are plotted in the x-axis. And the lower side is the low frequency information, and upper side is the high frequency information. And this is nothing but the plot of the sine and the cos theta, sine theta and the cos theta that we are plotting. So it is not a difficult one, but positions are represented in the terms of sine theta and cos theta. And the top portion of this figure, it corresponds to the high frequency information, and the bottom is the low frequency information, and that is based on the sine theta and the cos theta. So one example is the river bank. So if I see the position of this word river, so river position is 0 and position of the bank is 1. And if I consider the dimension of the model is 6, so we can determine the positional encoding of the river by using this formula. So we have 6 dimensions. So sine theta, cos theta, sine theta, cos theta, sine theta, cos theta, we are determining. So that is for the river we are determining. That is the positional encoding we are determining. And similarly, the bank also we are determining the sine theta, cos theta, and the dimension is 6. So the dimension of the vector is 6. So let dimension is 6, and if I consider position is equal to 0, so position vector P is 0, we can determine like this. And for P1, the position number 1, we can also determine P1 also we can determine. That is the position vector 1 and position vector 0 we can determine. And ultimately we can get the vectors PE0, that vector is 0, 1, 0, 1, 0, 1, that we can determine. And PE1 also we can determine, that is actually 0.84, 0.54, 0.999, 1, 0.9991 we can determine. So this position vector we can determine. And after having the positional encoding, the final embedding, that is the final embedding vector, final embedding vector is x dash is the final vector embedding. So what we are doing, the contextual embedding vector is added with the positional encoding. The contextual embedding vector is added with the positional encoding, and that is I am getting the final encoding. So final encoding is the x dash is the final encoding, and it has 2 components. One is the contextual embedding and another one is the positional encoding. So 2 components, one is the contextual embedding vector and another one is the positional encoding vector, and it is added. So you can see what is the meaning of this sine and cosine. So if I consider this PEIJ, so I is the index position of the vector in the embedding, and J index position of the elements in the vector. So in this expression, I represents the position of the vector, position of the word in the sentence we are considering, and J is the index position of the elements in the vector. So J is considered like this. So I is the position and J is the index position of the elements in the vector. So again we are considering sine theta and cos theta. So you can see here we are just plotting sine theta and cos theta. So in I, actually the different positions are available, and J is the position of the vectors, elements of the vectors. So if you see in uh, this values, if you see this row wise, if you see the row wise, the red colored box, that is for 0. The position 0, we have this the sine theta cos theta. You can see in the row wise. You can see the first row sine 0, that's sine 0 divided by 1000, 0 divided by 5. So position number 0 is considered in the first row. In the second row, we are considering the position number 1, second row. In the third row, we are considering the position number 3, we are considering, and that is represented by the sine theta and cos theta. So corresponding to the first row, we have sine theta, again cos theta, again sine theta, again cos theta, again sine theta, like this we are considering. Because dimension of the model is 5. Similarly, in the second row, we are considering the position sine theta, position, there is a sine theta function, we are considering cos theta, again we are considering sine theta, cos theta, and sine theta we are determining. That is corresponding to the second row. That is the position number 1. So I represent position, and J is the position of the particular element of the vector in the position vector that we are considering. So this is the embedding. We are considering the positional embedding. So why actually this positional embedding is important? So if you see this trigonometric expression, the sine x plus y is equal to sine x into cos y is equal plus cos x into sine y. We know this expression. Similarly, cos x plus y is equal to cos x into cos y minus sine x into sine y. And suppose if I consider a fixed offset is suppose k. So corresponding to this offset, if I apply this principle, the sine theta cos theta function, sine omega j I plus k, we can represent like this: sine omega I into cos omega j into k plus cos omega j into I plus sine omega j into k. And similarly, the cos also we can expand. Cos omega j into I plus k is equal to cos omega j into I cos omega j into k minus sine j into I sine omega j into k. And if I consider omega j is equal to 1 divided by 1000 j divided by d model, so in the matrix operation, we can consider sine omega j I plus k cos omega j I plus k, that is equal to, we are considering one matrix. That matrix is the rotation matrix. Cos theta sine theta minus sine theta cos theta. That is the rotation matrix into sine omega I into sine omega I cos omega j I. Sine omega j I cos omega j I. And that is multiplied with the rotation matrix. The rotation matrix is cos omega j k sine omega j k minus sine omega j k cos omega j k. So if I consider PEIJ, so position IJ, that position we are determining. So position IJ we are determining. So it is nothing but sine omega j I and cos omega j I. And after this we are determining position I plus k. Next position, another position I plus k comma j. So I have this one, omega j plus I plus k and cos omega j plus I plus k. And if you see position I plus k comma j is equal to RIK. RIK is nothing but the rotation matrix PEIK IJ. So what is the meaning of this? If I have the position IJ, position vector IJ, the position vector I plus k comma j, that can be obtained by rotation. So in the figure you can see, we know the position PEIJ, that position we have determined, and position PEI plus k comma j, that can be obtained by rotation. That is a rotation by angle minus 1 minus omega j k in the clockwise direction. So in the clockwise direction, I am doing the rotation and I am getting the PEI plus k comma j. So that I am getting. So that is the advantage of considering this positional representation, sin theta and cos theta. So any position we can consider by considering this rotation matrix. And this rotation matrix also we can do the learning. Again, we can apply the learning principle to learn the position matrix. And it is nothing but a rotation matrix. And we can find the embedding, position embedding I plus k comma j we can determine. From PEIJ that we can determine. Only thing we have to rotate by an angle. Angle is minus omega j k. By this angle we have to rotate. Then I will be getting the PEI plus k comma j. That is the I am getting. So you can see for all the elements, if I do j is equal to 0, j is equal to 2, j is equal to 4, in this case corresponding to this input sequence, how are you? We are determining these positions only by rotation. So Rk is the rotation matrix, and by rotation I am getting all other positions I am getting. So that is the concept of the rotation. And you can see all these rotations I can put in the matrix from all this. And after this, you can see Hi we are determining, that is nothing but the contextual embedding plus position embedding we are having. So we are considering the contextual embedding plus position embedding, because already I mentioned that the final embedding is nothing but the contextual embedding plus position embedding we have to consider. So this mathematics explaining now. So if you see this one, we are actually, again I'm showing, we are finding the attention score EI I plus K. We are determining attention score. We are determining, like it is the dot product between the query and the key and divided by model. And if I do the expansion of this, you will be getting this one. The attention you can determine I plus K attention score you can determine. So if you see this expression, first one is the token to token interactions. That means it is a content based alignment between Xi and Xi plus K. That is called the token to token interactions. If you see the second term, the token to position interaction, the token position interactions. So that means the token at I interacts with the relative position K of Xi plus K. So that is the token position interactions. Third one is position token interaction. So the position I interacts with the token Xi plus K. So that is the position token interactions. And finally, the position interaction you can get. So how the relative position K interacts with the absolute position I. So these interactions you can determine: token interactions, token position interactions, position token interactions, position interactions you can determine. So you can see we are having this one. So how are you use the input sequence, and you have the token embedding and you have the position embedding, and after this it is added. Already I mentioned that we have to add this one. After getting the final embedding, we are getting. So in this case, we are encoding both semantic meaning and the positional information also we are considering. Semantic meaning is also considered. There's a contextual meaning we are considering, and also the positional information also we are considering in this representation. So this is the final representation of embedding. So already I mentioned this. Without positional encoding, if I consider these two sentences, how are you doing? And another sentence is doing are you are how. Then if I only consider only the self attention, then in this case it will not be equal. Both will be different. But if I consider, so that is why actually we have to consider the positional encoding. So first we are considering the token embedding and also the positional embedding. And after this we are determining the key and the queries. So alignment scores are, we are multiplying. And after this we are finding the alignment score. And this is the concept of the positional encoding, the multi-frequency design. So corresponding to particular sine wave, you can see we have these different positions in the sine wave, and we can consider multiple frequencies for encoding we can consider. So you can see corresponding to this red color, corresponding to one red point, if you see the column, that column, you have the position of the element in the vector. Corresponding to another point in the sinusoidal wave, you have one element of the vector in that vertical line. You can see this is a vertical line, means it's a vertical. This is the vector actually, the positional vector, and corresponding to this red point of the sinusoidal curve, you have the one position in the vector. So that is actually the positional encoding by considering multiple frequency. And you can see we are considering multiple frequencies. In the left side, we are considering the high frequency, and the right side, we are considering the low frequency. In the left side, you can see, if I see the bottom of the figure, of the left figure, this corresponds to the low frequency, and if you see the top part of the figure, that corresponds to the high frequency. And corresponding to all the position of sinusoidal wave, I have the positions in the vector. The elements of the vectors are placed in the vector. That is actually the positional encoding. So this concept already I have mentioned. And finally, we are considering the layer normalization. That best normalization I mentioned in the beginning. So in this case, because we are having the sequential word, So corresponding to one sample, we are doing the normalization. So sample by sample normalization we are doing. So first sample is coming, we are doing the normalization. Second sample is coming, we are doing the normalization. Like this, we are doing the normalization of this. So for this, we are computing the mean, computing the variance. We are doing the normalization, and after this also we are applying the learnable parameters. So I am moving fast because I have to finish by 6:10. So complete encoder is something like this. So this is the complete encoder. So 6 numbers of encoder and the 6 numbers of decoders are available. So here you can see encoder part and the decoder part of the transformer. So we have 6 encoders and we have 6 decoders. So now let us overview of the encoder. So first part is the input is coming, input embedding is done, and after this also we have done the positional encoding, and both are added. And after this we are doing the multi-head attention we have done, add and normalization. So normalization means the this layer normalization we have done, and add means we are adding the residual connections, that is the skip connection we are considering. And after this again we are considering the feed forward network for the final classification, or I can say final decision we can consider. So first part is the encoder positional encoding we have done like this. First is the tokenization we have done. However, use the input sequence. After this we have done the tokenization. After this we have done the embedding, and also you can see the positional encoding in the figure. And this embedding, that is the token embedding, is this embedding is added with the positional encoding, and that is inputted to the encoder. So that means we are considering the positional encoding information, and one is the contextual embedding we are considering, and after this it is added, and that is the input to the encoder. And after this we are considering the multiple heads. Already I mentioned about the multiple heads, how to consider the multiple head. So we have to consider attention corresponding to head number 1, head number 2, head number 3. And after this, we have to do the concatenation of the heads, head number 1, or we have to do the concatenation of this. And finally, we have to consider the fully connected layers, that is the feed-forward network. So it has 2 layers. So layer number 1 has 2048 neurons. So first, actually, we are doing the expansion of this. So first, actually, we are doing the expansion of this. So it is now mapped to 2048 neurons. So input is 512, but now it is mapped to 2048. So it is the expansion is done. So if I do the expansion, what will happen? So we will learn more contextual information. So that means we are moving into the high dimensional space, and also we are applying the non-linearity. And after this, in the layer number 2, we are doing the compression. So that means in the layer number 2, we have only 512 neurons. So first we are doing the expansion, and after this we are doing the compression, and also we are considering the nonlinearity, the Rayleigh activation function we are considering. So what is the meaning of this? Actually, because of this we are learning complex patterns. So we are learning the complex patterns. So first actually we are moving to the high dimensional space, and after this again we are doing the compression, so that we can learn complex patterns. And this is the concept of the final network. So again, you can see the encoder is first we are considering this multi-head attention. After this, we are doing the add and normalization. After this, layer normalization we have done. Already I mentioned about this. Feed-forward network already I have mentioned, that is the 2 layers are available, layer number 1 and layer number 2. And after this again, layer normalization is done. And this is Y1, Y2 and Y3, that is the input to the second encoder. So we have considered 6 encoders. Now we are considering the input to the second encoder. So Y1, Y2, Y3, these are the inputs to the second encoder. Now come to the decoder. So this is the structure of the decoder. So you can see the decoder input is coming from the encoder also, and also the past sequence also it is coming as an input. So first again we are doing the output embedding, positional encoding we have done, but here we are considering the max multi-head attention we are considering. What is the max multi-head attention, that we will explain. And other things like multi-head attention, you know the multi-head attention, feed-forward network, you know about this. But important point is the max multi-head attention. What is this? So I have to skip this portion because time is less. So in this case, in the prediction process actually, we do it auto-regressively. So what is the meaning of this? Actually, it's a causal operation like in signal processing. So we have to predict the words, and this predicted word depends on the previously generated words. We cannot see the future words, we cannot see. So during in the encoder, it is possible to see the future words, but during the decoding, it is not possible to see the future words. But we have to predict based on the present word and also the predicted words. So future words are not available. So during the training, future words are available, but during the prediction, not available. So for example, suppose if I want to predict the first word, second and the third words are not available. And if I want to predict the second word, the first and the third word is first word is available, but the third word is not available. So like this, we have to consider. So that is actually the causal system. So it is an auto-regressive process. So you can see, if I consider how are you, I am fine. If I do the decoding of this, so embedding I, there is a new embedding for I. So first one is the I, but I do not know am and fine. That is the future token. I do not know about this. I should not consider this am and fine. After this, come to the next one, em. That is a new embedding for the m or m. I know I, because already I1 is predicted, I is predicted. So m we can predict based on I and also the other information. But the fine is not available, that is the future, so we should not consider this. And whenever we do the prediction for the fine, E fine, then we may consider the word I, we may consider the word M, we can consider. So that means during this causal process, we should not consider the future tokens, we should not consider during the prediction. So in what we are considering, again, you can see we are determining the attention value. And you can see Y1, W11, V1. The future tokens we are not considering, 0 plus 0 we are not considering. So you can see again we are considering attention. So the dot product between query and the queue, and after this we are doing the scaling and the softmax operation, and after this we are multiplying with the V1. So W11 V1, but M and fine is not considered, so the future tokens are not considered, so it is 0 and 0. In the second prediction, I is available. So now YAM is equal to W11 V1 plus W1, but fine is not available, so it is 0. And during the prediction of Y fine, we can consider V1, VI, VM, and V fine we can consider. So that is the meaning of the auto-regressive process. So for this we can consider a marks, something like that. So we already have the values S11, S12, S13, S21, S22, like this we have these values. And if I consider this is a marks matrix we are considering, so if I apply the marks, if you see that this value S11 infinity, infinity, S21, S22 infinity, S31, S3, S32, S33, this we are getting. And if I apply the softmax operation, then I'll be getting the weight value, W11 weight value, W21, W22, W31, W32, W33, and remaining is 0, 0. 0, 0 I am getting. Because I am not considering the future tokens, I am not considering. And this is the principle of the marks at the weights. So we are considering the masking. So these future weights are not considered. So W11 is considered, W21 is considered, W22 is considered, 31 is considered, 32 is considered, 33 is considered. But because of the marks, we are not considering the remaining. S12 is not considered, S13 is not considered, S23 is not considered. So now in case of the decoder, the cross attention is important, one cross attention. So what is the cross attention? Because we have to see the similarity between the sentences, two sequences. If I only consider the self-attention we are considering the same sequence we are considering. But if I consider multiple sequences, we have to see the attention between or the similarity between different sequences we have to consider. So for this, what we can consider, query is coming from the decoder and key and the value is coming from the encoder. So during the decoding or during the prediction process, the query Q is coming from the decoder and key and the value are coming from the encoder. Because we have to find the contextual meaning of different sequences we have to determine. In case of the self-attention, we are only considering only one sequence. In one sequence, we are finding the contextual meaning. But in the cross attention, we have to consider the similarity between different sequences we have to determine. So like this, you can see the query is coming from the decoder, and key and the value is coming from the encoder. So you can see already I mentioned the query is coming from the decoder, and key and the value is coming from the encoder. So it is the query is coming from the Dr. Nayak.
Yes, sir.
Hello.
Yes, sir. Yes, sir.
So how long I can take, up to what time?
Up to 6:20, sir. You can take
Okay.
6:20, sir.
Okay.
I mean, the time is actually 6:10, but you can continue up to 6:20, sir.
Okay. So you can say the natural calamity. This is the earthquake was in between.
Yes, sir. Yes, sir.
So you can see we can consider this here. The Q actually the query is coming from the encoder, from the decoder. The query is coming from the decoder, and the key and the value is coming from the encoder. So you can see Q1 is coming from the decoder, and the query and the key and the value is coming from the encoder. So corresponding to this, I am fine. You can see how the contextual information of two sentences, that is actually the cross attention we are determining. So in the self attention, query, key and the value are generated for each word in the same sequence. So query, key and the value are generated from the word of the same sequence. But in the cross attention, query is coming from the output sequence, that is actually from the decoder, and the key and the value is coming from the input sequence, that is from the encoder. That is the difference between the self attention and the cross attention. And this part you can see that if you see the decoder received the two input, one is the encoder output we are having. You can see one connection I have shown. So if you see this connection it is coming from the encoder, and also this input is also coming. These two inputs are coming. So encoder output we are giving to the decoder, and target sequence also we are giving. And after this, you can see we have to consider this key, query, and the value. So encoder output serve as a key, and value uh, and value, and while decoder process the embedding serve for the queue. So already I mentioned about the queue and the query and the value. So this part I'm skipping. So this part I'm skipping. So directly I can show this figure. You can see how we can do the predictions. So in the encoder, what we are considering, how are you? That sentence we are considering. And you can see SOS means the start of the sentence. In the decoder, that is coming, how are you is coming, and we are determining the contextual embedding, the contextual meaning we are determining. And first, I am predicting I. So in this case, we are considering the marks multi-head attention we are considering. So that means the future token considering. After this, based on I, if you see input is again I am giving the input I is the input to the next stage. If you see the next stage, in the next stage I am giving the input is I. This I is coming, and we are predicting M. And in the third stage, I am giving I am. These two words I am giving, predicting the fine, that I am doing the prediction of this. And finally, I am fine. That is the EOS means the end of the sentence. I am doing the predicting. So input is coming from the encoder. The input is coming from the encoder. Input is coming from the encoder. And also I am giving the inputs. This input also I am giving. And I am doing the prediction. The prediction is I am fine. The question is, how are you? That is from the encoder. That is the question. How are you? So in the set GPT, if you see, we are giving some questions. If you see the set GPT, how are you? So some questions, some answers are coming. So like this, they consider the encoder decoder concept. So how are you? I am giving, and set GPT is giving the I am fine. So that is actually one concept of the LLM, the large language model. So like this, we consider. So I'm not going to discuss about this, how it is done. So what is the difference between the self attention and the cross attention? If you see the matrix here, A, that matrix. So in the vertical side, I am considering I am fine, and in the horizontal side, I am going showing how are you. So first, you can see I and you are related. The word I and the you are related. So the attention score is 0.7. I am having 0.7. After this M, M and R are related. M and R are related. So attention score is 0.85 I'm getting. And after this, fine and how are is related. Fine and how. So I'm getting the attention score of 0.5 I'm getting. So you can see how I'm getting the attention score. I and U are related. So I'm getting 0.7. M is related to R. So I'm getting 0.85. Fine is related to how. So I'm getting 0.5. So you can see in the self attention and difference between the self attention and the cross attention, tokens within the same sequence we are considering in the self attention. But in the cross attention, tokens across encoder and decoder sequences are considered. So that is the one fundamental difference between attention and the cross attention. And also in self attention, we are considering the encoder layer and the decoder is the max self attention we are considering. And in the cross attention, we are considering decoder, cross attention, sub layer we are considering. And if I consider Q, K, and V, so in case of the self attention, Q, K, V all are from the same sequence, but in the cross attention, Q are coming from the decoder and K and V are coming from the encoder. So that is the difference between the self attention and the cross attention. And directly I will come to the vision transformer. So what is the vision transformer? That is actually for computer vision applications like the problem of image classification or mainly sometimes object detections. So now I will explain in image classification how you can consider the vision transformer. So idea is same idea. So it is also the encoder concept. Decoder is not required because the problem is the classification problem. So it is not, the decoder is not required. We only need the encoder. So in this case, this was developed by the Google researchers. The name of the paper is An Image is Word, 16 by 16 words, transformer for image recognition at scale. And vision transformer is only used for the images, not for the words. And what is the problem of the CNN? If I consider the CNN, generally we get the local information. If I consider different filters, we are having the feature maps. But the global contexts are missing. So what is the global context? So that is why we may consider the vision transformer so that we can see the whole image using the self-attention, and we can find a global context also we can determine. In CNN, we have to consider multiple filters, but in that case also, it is not possible to see the global context. So in the image, in the vision transformer, images are split into small pieces. These are called the paths, or it is treated like the sequence. And after this image paths are processed like the NLP. So already we discussed about the natural language processing. So we have to consider the path sets, image paths, and after this we have to do the processing. So how we consider, if you see this input image, so image size is 48 cross 48. So suppose image size is more than this, we have to scale down. And if the image size is less than this, we have to scale up. And if the image is a grayscale image, we have to do the replication of the R channel, G channel, and the blue channel. So the channel should be replicated to get the three components, R component, G component, and the blue component. If I have the grayscale image, but for the RGB image, we can consider this 48 cross 48. And we are considering the patch size is 16 cross 16. And number of patches will be 9. So 9 patches we can consider. So you can see we have the 9 patches. So these paths are converted into 1D vectors. The paths are converted into 1D vectors. So patch size is 16 cross 16, and we are considering the RGB image. So dimension is 16 cross 16 into 3. So if I see the dimension of the 1D vector, so it will be 16 cross 16 cross 3. So it is 768 into 1. So that is the dimension of the vector, 768. And after this, corresponding to this 768 values, that is the pixel value, what we can consider, we can consider this vector, we can consider the reshape vector, we can consider. So 768 value we can consider corresponding to one patch we can consider, that is a 1D vector. And that means the 768 tokens. So we can consider the 768 tokens or the pixel value we can consider. And since we have 9 patches, so to get 9 numbers of 1D vectors, so that means we have 9 patches and 768 into 9. that we have to multiply 768 into 9 for the 9 pets. After this, what we are doing? We are doing the linear projections. So y is equal to x w plus b. So this is a linear projection equation that is done by neural network. So input layer has 768 neurons. Already I mentioned about the tokens. So 68 pixel value. And after this, we are compressing it to 512 neurons. So because of this compression, we are eliminating the redundant information. So we are doing the compression of this by using this linear projection. So input layer has 768 neurons, but in the output, we have only 512 neurons. So transformer process all the tokens in parallel. So in parallel, we are doing all the tokens parallelly. So spatial information is lost. So that is why also we have to do the position embedding, and number of position embedding vector is equal to number of patches. But in case of the NLP, we consider the sine and cosine function. But in this case, we are not considering the sine and cosine function. For the vision transformer, we are considering the training of this. So position embedding are learnable parameters and initialized randomly and updated during the training through backpropagation. So it is unlike the NLP, we consider the sine and cosine function, but in this case, we are considering the learnable parameters, position embeddings, and it is randomly initialized. And after this, we are applying the backpropagation training to get the position embeddings. So like this, you can see first we are doing the linear projections. So linear projection we have done. So we are having 512 into 1 dimension. After this, randomly the position encodings. And after this, we are having the position encoding pads embedding 512 into 512 into 1. So after this, we are having. So that means we are considering the positional embedding also we are considering. So you can see the same thing we are considering. First, the input image. After this, we are doing the patching. After this, we are flattening. After this, we are doing the linear projection. Flattening means this array is converted into vector. So the image array is converted into vector. That is the patch is converted into vector. And size of the vector is 768 cross 1. And after this, we are doing the linear projection. So dimension is reduced. So it is 512 into 1. After we are considering the position embedding. And this, the original embedding plus positional encoding, this is added. And finally, I'm getting the position encoded embedding vectors I'm getting. And that is the input to the encoder. And one extra learnable token is also considered. So it is used for the classification. So like this, finally, in the vision transformer papers, you can see input size is 224 into 224. So patch size is 16 cross 16. So number of patches is 196. And each patch size has 768 values. So it is 1D vector. The vector is 768 cross 1. And after this, we are doing the linear projection. So after the linear projection, 768 dimension is converted into 512. And after this, we are considering the positional encoding. And after this, the linear projected vector and the positional embedding vectors are considered. That is, they are added to get the final embedding. And that is the input to the encoder. And for the final classification, we are considering multi-layer perceptron, MLP we are considering, and multiple heads we can consider. So this encoder working, I am not going to discuss about this. And finally, we are considering the normalization and multi-layer perceptron MLP. We can consider multi-head also we are considering. So we have to consider multiple heads, and we have to do the concatenation of the heads, head 1, head 2 like this. So this is the structure of the transformer. Here the decoder is not important because we have to consider the classification problem. So the concept is image is divided into patches, and after this we have the tokens like the NLP. Also we have to self attention also we have to determine, and after this we have to consider the position encoding also we have to consider, and after this we consider the multi-head attention we have to consider. So multiple heads we are considering, and after this in between we are reducing the dimension of the vector. So by using the projection, linear projection, we are reducing the dimension. And finally, we are considering the multi-layer perceptron head, MLP head, for the output classification. So multiple heads we are considering for all the attentions, and MLP for the final classification. So this is the of the encoder. So some of the concepts are available in my this computer vision books like backpropagation and the neural networks. And this book also, this some of the figures I'm taking from the another book, Advanced Machine Learning and Deep Learning Algorithms. So this book will be coming into the market very soon. So some of the figures, it is actually I should not published publicly. So because these are copyrighted figures. So in the second book, you can see all the discussions about the transformer and all the deep learning concepts. And already he mentioned about that these two NPTEL courses. One is machine learning and deep learning, and one is computer vision and image processing. So you can see some of the videos, related video from these two courses, NPTEL courses. And this is for the faculty members who wants PhD students. So generally we do for the students. So come for the research. Research is not a difficult, just you come and you do the research. So faculty members in IIT and NITs, they do like these type of things. And students, you can see the students there. So thank you. Thank you for this. Hello.
Yeah. Thank you so much, sir, for a wonderful talk on transformer. I hope participants have got ideas on transformer, all the components of the transformer, which is very difficult to understand. Sir has explained beautifully, starting from each of the components of the encoders and all. So I hope participants have got a lot of ideas and they can correlate the concept with the vision transformer. And sir has also discussed the mathematical concepts in detail. I mean, step by step. So participants, if you are having any queries, you can write it in the chat box so that I can summarize and I can directly. Yeah. Thank you very much, sir, for your informative session. Okay. Sir, is it compulsory the image size 48 cross 48?
No,
It
it
has
is not.
already seen.
It is not. It is not compulsory. It is not
Yeah.
compulsory.
Very nice lecture, sir, from Dr. Aditi. While calculating the attention score in formula, if we have taken linear attention approximation instead of quadratic attention, will it give same output or it will change drastically?
No, no. Quadratic attention will give the different meaning.
Oh. So what is generalized neighborhood attention and rank augmented attention?
So if you have any questions, then you can later also discuss with me, because
Yes, yes,
mail
yes.
IDs are available, because I think next session will be starting at 6:15 or 6:10.
620, sir. Yes, sir.
6:20, and you tell the next speaker that there was a natural calamity, something like this. So because of this, there
Yes,
is
sir.
a 10
Yes.
minutes delay of this.
No problem, sir. Yeah, very informative, sir. Very well explained. Yes. Sir, what are the what are the challenges are present when we implement deep learning model on own created data set?
Pardon.
Sir, one question from Dr. Lalita, that what are the challenges we face while implementing deep learning models on the own created data set?
The main problem is we need huge amount of training data. Deep learning has the main problem, because if you have a huge number of training data, then you can apply these deep learning algorithms. Suppose in case of the medical image analysis, it is very difficult to get the huge amount of training data. Then it is very difficult to apply that these transformer models and all these models. It is very difficult to apply. So generally, we consider the semi-supervised training. In semi-supervised training, what happened? We have few number of trainable. We have few training samples, not many, and maximum unlabeled data. So only few labeled data and maximum unlabeled data is available in medical image. So in this case, you can apply the semi-supervised learning. So only few labeled data are available and maximum unlabeled data are available. Then in this case, you can apply the semi-supervised learning. So in deep architecture, that is the main problem. So if you have huge number of training data, then I think that is not a problem. You can apply deep learning algorithms. But
Yes, sir.
in medical case, I am facing the problem because it is very difficult to get the label data. So since the label data is not available, then you have to apply some semi-supervised learning techniques.
Sir, can we get access to your slides?
No, some of the contents I can give, some of the figures I cannot give because it's from my book. This is copyrighted.
Yes, yes, yes.
So
So
I
when
can
to
give.
expect? Uh, yeah, when to expect?
Hello, hello, hello.
Yeah, yes, sir. Yes, sir.
I can give some of the, because these are available in the paper, the transformer papers. It is available, but some of the figures are from my book. So these figures
Yes.
are copyrighted figures. This book will be published by CRC Press. Your voice is not audible, Dr. Nayak. Your voice is not audible. Your voice is not audible. You are not audible. You are not audible.
When to expect your advanced ML book?
So by March, April, you can get.
So participants, yeah, by March, April, probably you'll get the new book. Yeah, thanks. Thanks for the
This book I
informative
cover all
sessions.
the concepts like federated learning, all the knowledge graph, LLMs, all the things I have covered in that book. So this is around 500 pages book. So you can see that book.
Okay, sir. If you're having any other queries, please drop an email to sir. Sir will get back to you. Yeah, I think, sir, there are no other questions from the participants.
Okay, then I can
Yeah,
log out from the system. Is it okay?
sir. Yes, sir. Yes, sir. Yes.
Okay, thank you all the
Okay.
participants for attending this session. In between, there was a problem. That is,
And no problem, sir. But still, you have managed, and
even my
still you are
transformer
able
could
to.
not predict that one also.
Thank
So,
you, thank you,
okay.
thank you very much, sir, for accepting our request, for sparing your valuable time with us. A participant could at least got to know about many things from you, sir. And now, I mean, they can also watch your videos on NPTL, from where also I got to know about you. So
There will be
thank you
another
very much.
NPTEL course in July 2012, 2016, deep learning, only on deep learning.
Yes, yes. Okay, sir. Thank you very much, sir. Namaskar. Yeah, participants will move on to our next session. So next session will be delivered by Professor Dwarika Nath Mahapatra. Yeah, hello, sir. Good evening.
Hello, Deepak. Hello, Deepak. Good evening, Deepak. How are you?
Yes, sir, I'm doing well. Hope you are also doing well. Participants
Yes.
are waiting for your lecture, looking forward to your lecture. So,
Okay, that's very good.
yeah,
Okay.
yeah,
So, shall
participants.